Okay, so let us continue. So we were talking about finding the fittest parents. Rowlett wheel is one of the commonly used methods to select the chromosomes to be treated as fittest parents from the pool of fit parents. Um, by now you have understood that initially we created the initial chromosomes randomly. Then we may have a mechanism to use those bits to compute our um, fitness function, and based on that fitness value we decide upon which parents to get picked for the next generations. We do not take all the parents, so that means that we are leaving out those solutions which do not have the you know capability to take us to the optimal solution. We may not be picking up the string of or the bit string of the weights which are likely not to give us the optimal value of the error, the minimal value of the error. So we leave out those strings and we pick up only those possible strings which are likely to take us to the best results. So the fitness values of all eligible chromosomes with fitness greater than a threshold are added, and a random number decides the fittest parent. Okay, so here, because of its high favorable chance due to its individual large fitness value, you can always say that if let us say my solution lies at a point 111, which is representing a bit string, and suppose I have reached somewhere close to this 111, maybe my values were not so binary as zeros and ones, but my values were even real numbers, and suppose I'm having 0.9, 0.9, 0.9 as my string right at the previous generation, then you would understand that we are actually close to the point 111. You can always say that, point 9, point 9, and point 9. This point is very close to the point 1, 1, and 1, right? So we would say that this is about the fitness of the values 0.9, 0.9, 0.9. So also if you look at one more string, say 0.2, 0.2, 0.2, and if I'm defining its fitness, the fitness of this string as its closeness to the point 111, right? So is far from point 111. Okay. Which particular string is fit? If I am defining my fitness value as the distance or the negative of the distance, I'm taking negative of the distance of the point from 111. If that is the case, then which will be more fit string? I can always say that the first string was P1, okay, and the second string is P2. So which string is more fit? Will P2? So fitness value is has to be larger, right? So I can say that fitness value of P1, okay, how much is it is going to be? Fitness value of P1 is greater than fitness value of P2, is it not? So fitness value of P2 is minus, how would it be? So negative is also in the sense of finding the larger one. Can you compute the distance of 0.9, 0.9, 0.9 to 0.1, so to 111? Somebody can give these values? So it will be square root of 0.1 square plus 0.1 square plus 0.1 square. So the distance of P1 from 111 would be how much? It will be square root of 0.03, is it not? Yeah, so square root of 0.03 should it be? So the distance, the fitness value of P1 would be minus of square root of 0.03, is it not? So fitness value for P1 would be negative value of square root of 0.03. And what will be the fitness value of I'm telling you why this is negative. It is because we always try to revert or reverse the entire landscape of search. Now in the context of chromosomes and genetic algorithm, the context says that we always look for fitter parents or for fitter chromosomes. Fit means maximum. So any problem can be represented as maximization problem, even if it is a minimization problem. Like here in this case, we want to reduce the distance. But reducing distance is a kind of minimization problem. And when I want to represent this as a maximization problem, what am I maximizing? It is actually the negative. So let me find out the fitness value of P1. So fitness value of P1 is actually equal to minus of square root of 0.03. Now, can we find fitness value of P2? What is it going to be? What is this value? So 0.8 square plus 0.8 square plus 0.8 square. Does it mean 0.64? Should it be 0.064 plus 0.064 plus 0.064? Can you calculate this value? So this is going to be minus of square root of 0.8 square plus 0.8 square plus 0.8 square. Can you find out? Anyone? So 1.38 somewhere around. So I will write it as this. This will be 0.8 square, that is 0.6064, right? Plus 0.064 plus 0.064. That will be the fitness value of P2. So P2's fitness value is minus 1.3. Okay. And what is minus square root 0.03? Could somebody calculate? 0.03 square root. 0.173. Okay. So this is equal to minus 0.17. So which one is larger? Which one is larger? Just 1 minute. So minus 0.17 will be larger as compared to minus 1.38. 1.38 minus 1.38 is the fitness value of point P2, and minus 0.17 is the fitness value of P1. So fitness value of P1 is larger. That means the 0.9 is closer to 111. We are close to the optimal solution. So this is a genuine question, why we have taken the distance as negative for fitness value. Since we want the distances to be reduced, right? So how are we posing this problem as? We are posing this problem initially as a minimization problem. We want to find the minimum, as we wanted to find out the minimum of the error earlier. But to just maintain the terminology of the genetic algorithm, we can make use of the reverse or negation of the values which we want to minimize. So when you say negative, it will actually be turning out to take the form of a maximization problem. And fitness value is expected to increase all the time. We are not saying weakness value. We want fitness value. It is not a weakness value. We do not want somebody to become weak and weak and weak every day. So we do not want to pose problems here as minimization problem. We want to say that the chromosomes or the genes should become stronger and stronger daily. They should evolve to the betterment. That is why the negative of the distance. But there is no stopping, even if you define or pose this problem as a maximization, as a minimization problem, then you do not have to define a fitness as a negative value. If you define this as a minimization problem, then you as a programmer would be very cautious about seeing that the fitness value is also minimized. Okay. So calculation of fitness value is quite straightforward here. Here we are trying to just find out whether a given bit string, a chromosome defined by P1 is more fit to reach 111, where 111 is the chromosome which is the fittest, I would say. This is a point where ants are going to find some kind of sugar. And if some ant is at a point 0.9, 0.9, 0.9 is really close to the solution. But an ant who is at 0.2, 0.2, 0.2 is far from the sugar, right? So that is just a kind of representation of the chromosome as a point in an n-dimensional space to understand what we mean by search and what we mean by being closer to the optimal value. Okay, so P1 is a chromosome defined by 0.9, 0.9, 0.9, and then we are calculating the fitness as negation of the distance of this point from the optimal solution. So I would say that its fitness value is minus 0.17. This is having a distance of 0.17 from the optimal solution, while the other chromosome 0.2, 0.2, 0.2 is considered to be less fit because its distance from the sugar for this ant is very large. It is 1.38, right? And if you represent this distance as a fitness value, this fitness value will be minus 1.38. So minus 1.38 would represent a weaker chromosome and minus 0.17 will represent a stronger chromosome or a fit chromosome to participate in the next offspring. Is this okay? Fine. Is the calculation clear, Venkat? Okay, so now we are going into the some computation for finding out which parent should be considered for the for the next offsprings. So what we do is, let us say we have some five chromosomes, and let us say their fitness values are computed through different mechanisms. Say 2, 3, 4 and 5, 4, 5 and 6, right? So there were 5 chromosomes whose fitness values were different. One chromosome has 2, one chromosome has 3, 4, 5, 6. What we do in order to find the fittest chromosomes would be to find their cumulative probabilities. Okay, we first arrange the chromosomes in the order of increasing fitness value. Okay, so then we find the cumulative frequency of their fitness value. So we keep adding. 2 plus 3 is 5, 5 plus 4 is 9, 9 plus 5 is 14, and 14 plus 6 is 20. Okay. And then we calculate their probability. So the total fitness of all the chromosomes is 20. We find out the probability of each chromosome's fitness. You know the definition of probability. It is the number of favorable chances divided by the total number of chances. So 2 by 20, 3 by 20, 4 by 20, 5 by 20, and 6 by 20 are the chances of each chromosomes from 1 to 5 respectively to get selected, right? So who is more fit parent? A chromosome with the value 6. Fitness value 6 is the best chromosome to be picked up. We can always say the one with the fitness value 5 and the one with the fitness value 6 must be picked up as the fittest parents, because they will be representing the best solutions reached so far, because they are very, very close to the optimal solution. But we do not do this way. We do not pick up the chromosome 4 and 5 for their fitness values 5 and 6 respectively. We rather go for their, contributions in terms of the cumulative probability. So cumulative probability would be 0.1, 0.25, 0.45, 0.7. Why do we get 0.7? It is 0.45 plus 0.25, right? This frequency and this cumulative frequency, 0.45 plus 0.25 gets added to 0.7, and 0.7 and 0.3 will get added to 1. Now what do we do? This is again a mechanism of selecting the fit parent. Okay, so suppose we have these 0 to 2 and 2 to 5, 5 to 9, 9 to 14, and then 14 to 20. So here it is, a complete circle is defining 20 such probabilities. Okay, so then we divide each probability in its zone, right? So 2, 5, this one 5 to 9 is actually having its representation equivalent to 4 units. The third chromosome has fitness of 4. So it is like a wheel of fortune, you can say, where we can roll this wheel, or otherwise we just find a random value between 0 and 1. So if suppose the value comes out to be, let us say, random value we create, and suppose this comes out to be 0.6. So where should this 0.6 be? That means this 0.6 is representing the Rowlett wheel's third chromosome, right? The fourth chromosome. So the fourth chromosome is this one. So the arrow will come out to be somewhere in between 9 and 14. If that is the thing, if the random number is 0.6, the arrow comes somewhere here. If you consider this to be a kind of wheel that is moved freely and then it stops at one point randomly. Suppose this is 0.6, then what do? We pick up this parent number 4. Again we start using it, and then suppose we get the random value as 0.9, then we pick up the parent 5. But if we get, let us say, random value as 0.1, what will happen? Or maybe 0.15, sorry. If suppose this random value next time for the second parent selection comes out to be random value as 0.15, which one should we pick up? That means 0.15 will be somewhere between this, in this particular probability zone. So 0.15 will be in this second one. Cumulative frequency gives us a higher part of the range. So 0.15 is larger than 0.1 and is lesser than 0.25. So I would say that instead of selecting the sixth parent, I would be selecting 4 and 2, right? Because my random number has generated 0.6 and 0.15 to get selected these two frequencies, 0.7 and 0.25. Because they are the upper bounds on these numbers, 0.6 and 0.15 respectively, right? Yeah, 20 should be there at 0. Yeah. So random could be any value between 0 and 1 because we have already taken up the proportions between 0 and 1. So basically this cumulative probability is calculated so that our random number can support us between 0 and 1. Otherwise, you could have created a random number between 0 and 20. That also could have been a similar mechanism. And then you would have seen where this random number falls. Okay. So why randomness? Why aren't we picking up 4 and 5? Because there may be some redundancy in their solutions. They may be representing good solutions, but they may never give us a new combination to explore further a little far away. They may give us a new combination to explore a very close by area, right? So exploration requires us to have those two parents which are fit but not almost very fit. We do not go greedily in selection of the parents. We go a little less greedily in selection of parents. You can see that fitness value of the second parent is 3. Fitness value of the fourth parent is 5, which is good. Fifth parent is good, but second parent is not that good. But this kind of heterogeneity in genetics may help, that people would have actually found out in biology. But here also we rely on the random number generator to give us a way to pick up the parent. Okay. Yeah. So we are not multiplying the random number value with the fitness value. We are only seeing that this random value is 0.6. 0.6, let us say we created 0.6, is less than 0.7 and is also greater than 0.45. So this 0.6 is anyhow greater than 0.45, right, but less than 0.7. So we will say that this number 0.6 will correspond to the fourth parent. Have you understood this? Fourth parent will be supported by this random number 6. It is because my value 0.6 is lesser than 0.7 and larger than 0.45. So I would say that the number or the kind of arrow for this fortune wheel got me selected fourth parent. Okay, and suppose with the second random value 0.15, we get this random value. Let us say our wheel of fortune is stopped where I have this random value 0.15. So you can see that 0.15 is less than 0.25, but also it is larger than 0.1, right? So I would always consider this 0.15 to be falling in the cumulative frequency zone of second parent here, right? So this is the part where this 0.15 random value would take us to. Okay. So ideally we should take fourth and fifth parent because they both are the maximum fit parents, but it has been observed by the researchers that if you go greedily, these algorithms will not help us much. How do you say that this may not help us much? This you had also seen in your gradient descent algorithm, right? In the gradient descent algorithm, what had happened, you had taken the greedy step in the steepest descent direction. In that steepest descent direction, You took the step greedily, but you landed in the local optima. So by being greedy, it doesn't guarantee that we will be landing in the lowest ever point, or we call it global minima. That is where more randomness and less greediness is adopted in the evolutionary algorithms like this. Suppose the random value was 0.85, then where should it go? 0.85 is larger than 0.7, right? And it is less than 1. That means in that case, because randomly we are able to select the fittest parent, then we don't mind taking it. Then that means with 0.85, we would go and select the 5th chromosome, okay? We may not be getting the fittest parent with 0.15, as I showed you that with 0.5 I may be picking up the second parent, okay? But that itself will give us a way to explore the search space more beautifully. If we go more greedy, we tend to stagnate at one region of the search space. Then we do not have more capabilities to explore. Is it not? We will stagnate at that place if there are 2 parents. So we need to do this kind of random search many times, right? So we will keep on picking pairwise parents by using the same random process, and then we will apply the crossover and mutation operations. So why parent 5 with 0.85? Yes, 0.85, because suppose your random number is 0.85, right? Then what has happened is that 0.85 is lesser than 1. You focus on the cumulative probabilities, right? So 0.85 is lesser than 1.0 and is larger than 0.7. The cumulative frequency of 4th chromosome. Okay, that is why I am not taking 4th chromosome to be picked with 0.85, right? We should choose parent 6 for, no, not parent 6, it is parent 5 with fitness 6. So there is no parent 6, there are only 5 chromosomes, and with 0.85 we have the selection of the 5th chromosome. Okay, if we had something like 0.65, what will happen with 0.65? Somebody can tell? With 0.65, because it is lesser than 0.7 and larger than the previous chromosome's cumulative fitness value, right, 0.45, then we select in that case with 0.65 the 4th parent. Okay. So, right, so we will continue with this in tomorrow's class, and then we will do some application of genetic algorithms. So I will have to stop it here because now they are scheduling another class. Fine. So we will meet tomorrow. Tomorrow definitely we have a class, right? So I'm closing this session here. So you work it out, and they will be uploading the videos and the slides afterwards. So go through this and then read something more on genetic algorithms, and then we will discuss more on this issue tomorrow. Fine? Okay. So mid-semester evaluation is going on, and it will take its own course of time. So do not worry, the results, when they are done, it will be uploaded. Fine? Okay. So all the best. So now we are closing it here. Have a nice day.